start. It's my pleasure to introduce Graham Smith from the Universidade Federal do Rio de Janeiro and a good friend of our department. And today he's going to lecture about the Kulkarni-Pinkall form and locally strictly convex immersions in H3.
Okay, thank you very much, Antonio. Thank you very much, everyone. I just want to thank everybody for having invited me to speak here today. It's always a great pleasure for me to visit my friends in Granada, and always a great pleasure to visit Granada, most definitely one of the most beautiful cities that I've ever been to. So it's a sort of homage to Granada. You can see in my title page a lovely photo of the Alhambra, and behind the Islamic geometric motif from inside the Alhambra. Now let's see if I can put this into full screen mode. So as Antonio said, I'm going to be talking about the Kulkarni-Pinkall form and locally strictly convex immersions in three-dimensional hyperbolic space. So before I start, there's a lot of geometric definitions that have to be made in order to correctly frame the problem. Since I don't know everybody's background, I'll just quickly go through all the geometric definitions. So here, H3 will always denote three-dimensional hyperbolic space. An immersed surface in H3 will be defined to be a pair where SE, where S is a smooth surface and E is a smooth immersion. When we have an immersed surface, we denote by NE its unit normal vector field. Now for me, everything is going to be oriented. So this normal vector field then is going to be the positively oriented vector field relative to the orientation of the surface and the ambient space. Once I have these objects, I can define the first and the second and the third fundamental forms of this immersion. These are defined using, for example, Locarno's book. The convention that I use when I define second fundamental form is that the second fundamental form of two vectors, xi and mu, is equal to the inner product of the image of xi under the derivative of E and the covariant derivative of n in the direction of mu. Now you'll notice that different people use different sign conventions. This is a bit of a nuisance when we're talking about hypersurface geometry, but this is a convention that I use. I find it convenient because it means that you're positive whenever you're convex, which seems to me to be intuitive. Now, I'm going to say that the immersion is infinitesimally strictly convex whenever the second fundamental form is positive definite. Usually people say locally strictly convex when this condition holds. Usually people say locally strictly convex when second fundamental form is positive definite. But very recently, a reviewer of one of my papers told me that this was ambiguous, because if you're dealing with non-smooth surfaces, then locally strictly convex means something slightly different. I realized, yes, he has a point. So from now on, I've decided I will call surfaces whose second fundamental form is positive definite infinitesimally strictly convex. Now I'm going to introduce the first really new definition, which is the following. I will say that my surface is quasi-complete whenever the sum of the first and the third fundamental form is complete. So the first fundamental form of a surface, as we all know, is the metric induced by the immersion. And we know that, and we say that the surface is complete whenever the metric induced by the immersion, that is the first fundamental form, is complete. So here we have a slightly different condition because we're using a slightly different metric, but observe two things. Firstly, the third fundamental form is always positive. So this chap here is always positive. And second, because the first fundamental form is always positive definite, we can be sure that this guy here is positive definite. But observe that this guy is bigger than the first fundamental form, which means that curves with respect to this metric are longer than curves with respect to this metric, which means you can go to infinity faster. So what that means is that completeness in this metric, 1 plus 3, is weaker than completeness in the usual metric, 1. That means that I can have surfaces that are quasi-complete but not complete, but not the converse. I can't have surfaces that are complete and quasi-complete. And I'll come back to that later. And we will also have need for the extrinsic or Gaussian curvature. Once again, there are different terminologies. People use different names. The Gaussian curvature means something else in other contexts, but all very well. In the context of this talk, I will call K, which is the quotient of the determinant of the second fundamental form by the determinant of the first fundamental form, the extrinsic curvature of my immersion. And I'm now able to define what I will call from here on a K surface. I will call a K surface a quasi-complete, infinitesimally strictly convex immersed surface, SE, which is of constant extrinsic curvature equal to K. And this is going to be the hero of the story that I want to tell you in this particular talk. Now, before I continue, I just want to say, if anybody has any questions, if anybody wants to ask me any questions, please do not hesitate to ask me your questions. I like audience participation. I like answering questions. And in fact, I'm quite likely to find your questions more interesting than what I have to say. Anyway, we now have to define a concept of Gauss map. And here we encounter the first interesting problem in hyperbolic geometry, which is how does one define a Gauss map for immersed surfaces? What's the natural definition for a Gauss map of immersed surfaces? Now, I know that half the people here know the answer to that question. It's a lovely, elegant answer, but I thought I would just make a little parenthesis for those amongst us who don't quite know the answer to that question. Now, I'm going to change my camera. So I don't know who's in charge, but can someone please spotlight my camera here so that everybody can see my paper, please. So anyway, suppose we have R3, and suppose we have two distinct points in R3, and suppose that we have vectors, NP, unit vectors, NP, and then Q defined over these two distinct points. So the problem is, how can we put these two vectors in the same space? And in R3, the answer is very simple, because R3 is flat. There's a parallel transport, which takes these things canonically to the origin. In that case, we don't have a problem. That means that we can define a Gauss map of any immersion taking values in R3 is simply the function that sends S, well, the composition that sends the surface to the unit bundle, which gives you your unit normal, and then translates you parallel manner to the unit sphere. In the case of R3, this is just the projection onto the second factor in the projection onto the fiber in the unitary bundle of the unit normal vector field. That's all very well. That's trivial. Now, in order to understand hyperbolic space, it's good to see the Gauss map of R3 in a slightly different way. The reason why I'm talking about R3 here is because it's easier to understand in the hyperbolic case. So what we do is the following. We define an ideal boundary for R3 to be the set of all geodesic rays, complete geodesic rays in R3. So here gamma is a geodesic of unit speed. And we divide this space by equivalence, where two geodesic rays, gamma and mu, are deemed equivalent if the distance between them remains bounded for all time. So what does that mean? Well, quite trivially, two different rays are equivalent if and only if they point in the same direction. So these two rays here are not equivalent, whilst these two rays here are equivalent. In addition, it's a very easy way to put topology over the space of equivalence classes of geodesic rays, which is the cone topology. Cone topology is defined as follows. I take any open cone about a radial line in R3, and I say that a geodesic is an element of this open set if after a certain time it remains entirely within this cone. In this way, we can topologize a space of equivalence classes of complete rays in R3, and it's straightforward to show that this space of equivalence classes is homeomorphic to the unit sphere, where any ray is identified with its direction. Now, with this parameterization, we can see the Gauss map of R3 in a slightly different way. The Gauss map now can be conceived of as a composition, where you have the unit normal vector field, which sends my surface into UH3. Given a unit vector, I then have the geodesic ray that leaves from that vector, and that defines a point. Oops, sorry, this should be R3. That defines a point in the ideal boundary of R3, which I identify with the sphere. Now we're in R3, so everything is trivial. So this is actually nothing other than the parallel transport. But the point is that this is a construction which is entirely intrinsic to R3 and does not use parallel transport at any time. And as people who work with hyperbolic geometry know, this is also applicable in hyperbolic space. So I define UH3 to be the unit sphere bundle over the ideal boundary, and yes, I introduce what I call the horizon map. And now the horizon map is this function which sends a unit sphere bundle over H3 to the ideal boundary of H3, which we recall is defined to be the space of equivalence classes of complete geodesic rays, and which sends a unit vector, so the derivative of a geodesic ray at 0, to its point at infinity. So there are various names for this map throughout the literature, and the reason why I call it the horizon map is that the image of any vector is a point at infinity towards which it's pointing. It's the point at infinity that it's looking at. So if you believe that the Earth is a disk, like unfortunately many people in Brazil currently appear to do, then it is quite literally the horizon. So here is a schematic. Here is the schematic picture of the horizon map. So I have my unit vector here. I have my geodesic here, leaving my unit vector and landing at this point in the horizontal plane. I'm going to be drawing a lot of figures in the upper half space representation of hyperbolic space, quite simply because it's easier. In actual fact, it would have been better to draw pictures using the unit ball representation of hyperbolic space. So, very well. Now that I have an immersion, I can define its asymptotic Gauss map as follows. So I have my immersion SE, I have its unit normal vector field, and I compose the unit normal vector field with a horizon map. And that gives me a function phi E, which sends my surface into the ideal boundary. So here, the ideal boundary is schematically a plane here, because it's the complex plane, which as we know is an open subset of the Riemann sphere. So here I have my immersed surface, here I have my unit normal vector field, and here I have the geodesics leaving each normal vector, and here I have the asymptotic Gauss map, which sends my surface into the ideal boundary of H3. In particular, it's a well-known fact that it's a straightforward fact that can be proven using classical properties of convex subsets of hyperbolic space, that when this surface is infinitesimally strictly convex, this asymptotic Gauss map is a local diffeomorphism. And so the asymptotic plateau problem is, in a sense, the converse of this construction. The question is, can we construct a K surface out of its can we construct a K surface out of its asymptotic Gauss map? So we define an asymptotic Plateau problem to be a pair, S phi, where S is a surface, and phi is a local diffeomorphism from our surface into the ideal boundary of hyperbolic space. And we will say that two asymptotic Plateau problems are equivalent when they have the same up to diffeomorphism. And we will now say that the K surface SE solves the asymptotic Plateau problem of curvature K whenever its asymptotic Gauss map is equal to this function phi. Now, this is an asymptotic Plateau problem as was introduced by François Laborie, but it's good just to spend a couple of moments, I think, to understand a little bit the genealogy of this problem to see where it's coming from. So, as you know, the classical Plateau problem consists of prescribing an immersed surface from a closed curve in R3. So if I have a closed curve in R3, prove that there exists a minimal surface bounded by that closed curve. That's stage one in the genealogy. I think we can say that's the great-grandfather of the problem we're looking at here. The second step then considers the Plateau problem for surfaces of constant curvature for nonlinear notions of curvature, such as extrinsic curvature. So once again, one prescribes a boundary, but it turns out that in a nonlinear case, it's often necessary to impose the existence of what one calls an outer barrier, sigma hat, whose curvature is always greater or equal to the curvature of the surface you're looking for. When you have an outer barrier, you can prove in many circumstances the existence of a solution, sigma. The third step in this genealogy consists of moving this outer barrier to infinity. So imagine we're in a hyperbolic space. So this is the upper half of hyperbolic space here. And now I consider a curve in infinity. And the outer barrier will then correspond to an open subset of the ideal boundary of hyperbolic space. That's the third step. And the fourth step, which takes us to the asymptotic Plateau problem, this very general notion of asymptotic Plateau problem that was formulated by François Laborie, consists simply in forgetting the boundary. We now find ourselves in a situation where we are prescribing our surface purely in terms of its asymptotic Gauss map. So that's the Plateau problem, very general Plateau problem that François Laborie formulated. Now, let's see, just a second. Okay, so there are many, many known results for this problem. We can start, I think, with the work of Harold and Joel Spruck from 1994, which is a very strong result. It states that if omega is a Jordan domain in the ideal boundary of hyperbolic space, then for all k in the open interval between 0 and 1, there exists a unique solution to this asymptotic Plateau problem, omega ID. So what does omega ID here mean? Well, the surface is quite simply this open set, and the function phi is quite simply the identity map. So what that means is a solution to this asymptotic Plateau problem one can show is a surface, a k surface in hyperbolic space whose boundary is none other than the boundary of omega, because you see the boundary of S is the boundary of omega. Okay, and this is Harold's and Joel's result. Very nice result. Now, moving a little bit onwards, we get to this paper of my old supervisor, François Laborie from 2000, and there are many results in this paper. Now, one of his results is a uniqueness result, which states that for all k in 0, 1, there are in fact at most one solution to any asymptotic Plateau problem with curvature k. Now, this is interesting because this shows you that the asymptotic Plateau problem, as formulated by Francois, is indeed well posed. And this does actually resolve a little problem that one has when one studies the Plateau problem for K surfaces in hyperbolic space. For if we were to go back to the problem of Harold and Joel, in actual fact, in their paper, they show that there are two solutions. There are two solutions. Now, why is that? Because Harold and Joel, they define their problem in terms of the boundary. They say for any Jordan curve in the boundary of hyperbolic space, there exist two solutions to the asymptotic Plateau problem of that boundary curve. And why are there two solutions? Well, because a Jordan curve, the complement of a Jordan curve consists of two connected components. There are two Jordan domains. So what you discover is that there's one solution for each Jordan domain. With this solution that I've drawn here, the normal points inwards and points towards the Jordan domain that I've chosen. There is another solution whose normal points outwards into the other Jordan domain. So we see that this formulation of the problem that Francois made allows you, really allows you to select a single solution. So it's well posed. I should add at this stage, a lot of my surfaces here that I'm calling convex do not look remotely convex. This is because I am in the upper half space model of hyperbolic space, so that convex things do indeed not look convex. This surface here, for example, is convex in hyperbolic space. So I just want to mention a couple more results that Francois had, which are relevant to what I want to talk about today. So the first is that for all k in the open interval between 0 and 1, for every asymptotic Plateau problem S, one thing we can do is we can take a relatively compact open subset omega of S and then consider the sub-asymptotic Plateau problem given by omega and phi. So this is a slightly different problem to this one. And it turns out that whenever omega is a relatively compact open subset of my initial Plateau problem, there is in fact a solution. A bit of a strange result, but very useful. So you see, ideally, if one could show, one could exhaust omega by relative, if one could exhaust S by relatively compact open subsets converging to S, then if one could show that the sequence of corresponding solutions converges to something, then one would have solved the asymptotic Plateau problem in general. I'll get back to that. Francois also has a significant non-existence result, which states that if you have a finite subset of the ideal boundary of cardinality at most 2, then here we have an asymptotic Plateau problem, consistent taking my open set omega to be the complement of this finite subset, and phi is equal to the identity. And you can show that this Plateau problem has no solution when k is in 0 or 1. So when k equals 0, my omega is quite simply the whole of the ideal boundary. Sorry, silly me. Yes, sorry, at most 2, when the cardinality is at most 2. So I have some pictures on the next screen. So I'll just show you how that works. So imagine that you have an open subset, define an open subset whose complement consists of a single point. And this is used to define an asymptotic Plateau problem. Now, I can assume that this single point is a point at infinity, so that the open subset defining my asymptotic Plateau problem is the complex plane here. Then I can construct the foliation of hyperbolic space by horizontal planes, which, as we know, are all Horus fields. What do we know about Horus fields? We know that Horus fields have constant extrinsic curvature equal to 1. They are consequently solutions of this Plateau problem for k equals 1. But we want to show that there are no solutions for k less than 1. Well, observe that this is very close to the uniqueness result of Francois. In fact, what happens is, if we imagine that we have a solution of this Plateau problem defined by the complex plane here of curvature less than 1. Then using a geometric maximum principle, you can show first that it has to lie above one of these Horus fields, And the second, you take the first horosphere that meets it, and you get a nice contradiction from the geometric maximum principle. You need to perturb that argument a little bit to make it work properly, but that's the essential idea. So what you do is you show your surface is contained inside the horosphere and let the horospheres tend to infinity, tend to zero. Same idea works when you're dealing with a domain whose complement consists of 2 points. Omega has a complement consisting of 2 points, which we may suppose are 0 and infinity. We then take the geodesic, joining these 2 points in hyperbolic space, and we foliate the complement of this geodesic by equidistant cylinders from this geodesic. And then, as before, we can show that the solution to this Plateau problem has to be trapped inside every single one of these cylinders, which we show using a geometric maximum principle, and then we let the radii of these cylinders tend towards zero, yielding a contradiction. So, very simple geometric argument that Francois has to show that there can't be solutions in this case. So what do we know? We know that there are solutions in a large collection of cases. We know that there are some cases where there aren't solutions, but the question that Francois left open was exactly when are there solutions? So, hang on, I'm a little bit lost here. Give me a second. Oh. Yes, sorry. Now I know where I am. I'm sorry. As I said, I didn't see very well last night. So, this problem can actually be divided into 2 cases. Why is that? Well, it turns out that the ideal boundary of hyperbolic space has a natural conformal structure, which allows us to identify it with the extended complex plane, the Riemann sphere, C hat. We already see this in the upper half space representation of hyperbolic space, where most of the ideal boundary is represented as a complex plane. Now, what that means is, if I have an asymptotic Plateau problem, I can pull back the holomorphic structure of the image, and that gives me a holomorphic structure over my initial surface. And what that means is I can consider phi as a holomorphic map, sending my surface into C hat. And because phi is a local homeomorphism, that means it's never singular. So that means it's actually a locally conformal function from a Riemann surface into the Riemann sphere. Given that Francois has already proven uniqueness, in fact, it's sufficient to consider the case where S is simply connected. So if S is a simply connected Riemann surface, and we know it's not the sphere, we've already excluded that case, then it's going to be either the Poincare disk or the complex plane. So in fact, to study the Plateau problem in general is quite sufficient to consider the case where you have where S is either the disk or the plane, and phi is some locally conformal function from one of these 2 sets into the Riemann sphere, C hat. So I now quote a very old result of mine, which addresses the hyperbolic case. So the statement is the following. Suppose then that I have a locally conformal function phi, which sends the hyperbolic disk into the ideal boundary of hyperbolic space. Then my statement is that for all k in 0 and 1, in the interval between 0 and 1, there exists a unique solution E phi to the asymptotic Plateau problem defined by d phi, curvature k. Furthermore, you can do a little bit better. You can show that this immersion varies continuously in the C infinity log sense over D, so in the local C infinity sense over D, as phi varies continuously in the C0 log sense. So that's my older result that I actually proved in my PhD. So now we get to the more general case. Consider, now we get to the parabolic case. So this is the only case really that remains open. And we have this nice new result, which I proved in a paper that I was asked by Papadopoulos to write very recently. Let me see if I can find the paper for you. Here it is. So this is a paper in which this result is proven. So if anybody is interested, you can consult the result here, archive 2104-03181. So imagine that we have a locally conformal function phi, which sends a complex plane into the ideal boundary of hyperbolic space. And we suppose that it is not a cover of the complement of some set P whose cardinality is at most 2. Then we can show that for all k in 0, 1, there exists a unique solution to the asymptotic Plateau problem given by C phi. So this means that we have this is a complete solution to Francois' asymptotic Plateau problem, because as we already showed, this case here, where the image of phi is a cover of the complement of 2 points, those are exactly the cases that Francois addressed where he showed that there are no solutions. Now, it's interesting to compare this parabolic case with the hyperbolic case, because in the hyperbolic case, we don't just have existence, we have continuous dependence. But the technique of proof of the parabolic case does not actually give you continuous dependence. And I suspect that the solution E phi does not depend continuously on phi, but it would be nice to find examples which find examples where you have a family of conformal functions varying continuously whose solutions do not vary continuously. Another really interesting problem for me is to establish when the immersion is complete. Now, as I mentioned at the beginning, the solution to an asymptotic Plateau problem is a K-surface, and by hypothesis, a K-surface is quasi-complete, not necessarily complete. And so the question is, when is it that your solution to your Plateau problem is not just quasi-complete, but also complete? What are the conditions in the data phi for the solution to be complete? And for me, that's a completely open question. I have no idea how to answer that. So, how is it that one proves this theorem? Well, remember what I said about the results that Francois already has, especially this one here. That if I have a sub-Plateau problem, which is given by a relatively compact open subset of my surface, S, then I know that there is a solution. So if I could exhaust S by relatively compact open subsets, and if I could show that the solutions for each of these subsets in the exhaustion converge to a limit, then I would essentially have won. And that is exactly what we show. So the real result here, the real new result is this one, which I like to call the monotone convergence theorem. So how does this work? Suppose I have an asymptotic Plateau problem S phi. So S is a surface, phi is a local homeomorphism, and is not equivalent to this asymptotic Plateau problem, where I have which is the boundary of hyperbolic space, which is a complement of a finite set of points in hyperbolic space. Suppose now that I have a nested sequence of open subsets of my surface S, which exhausts S. And suppose that for all M, there is a solution to the asymptotic Plateau problem of curvature K defined by Sm. Now, as I said, if Sm is relatively compact, I know that the solution exists. So this condition here is superfluous because I assumed that my sequence exhausts S. Under these conditions, under these conditions, the sequence of immersions converges in a C infinity log sense to the unique solution of the asymptotic Plateau problem of curvature K. So this is really the result that makes everything work. Once you have this monotone convergence result, existence in the parabolic case immediately follows from the one result. But you see that one of the hypotheses of the monotone convergence theorem, one of the hypotheses of the monotone convergence theorem is precisely that my asymptotic Plateau problem not be equivalent to the complement of 0, 1, or 2 points in the boundary of hyperbolic space. And in that way, we see why this condition for the existence of solutions in the parabolic case is necessary, and we also see where Labourie's two counterexamples come from. So, how does one do this? Well, the first step is to use a remarkable compactness result, which Francois proved, I think, sometime in the 90s. The compactness result appears in a number of different forms across a number of different papers, but I would say that it's probably first formulated, shall I say, officially in this GAFA paper in 1997. It goes like this. In order to understand Labourier's compactness result, you have to forget that a K-surface is a surface in hyperbolic space. You have to look upstairs. You have to lift your surface to the unitary bundle and then work inside the unitary bundle and forget that there is something in the hyperbolic space below. So given an immersed surface SE, I can take its unit normal vector field. So as unit for normal vector field, we know it's an immersion into the unit sphere bundle over hyperbolic space. So I want to think of it as immersion. I want to forget that it is a vector field. So I'm going to give it a new name. I will call it E hat. So E hat is simply the unit normal vector field, now thought of as an immersion in its own right. So I call SE hat the Gauss left of SE, and it's an immersed surface in US free. Now Francois shows compactness results for these guys, for surfaces of this form, for surfaces which are Gauss lifts of K surfaces. Well, the first thing we observe is that this chap, the Gauss lift, is trivially complete if and only if my initial surface is quasi-complete, which is good because K surfaces are quasi-complete. So we already see in Labourier's compactness theorem very natural place in which a quasi-completeness hypothesis becomes necessary. One very curious aspect of, however, of the proof of the result I'm going to tell you is that there are other natural places where quasi-completeness is necessary, which is very nice. It shows you that quasi-completeness is the real condition. So now we get Francois' compactness result. He says the following. Suppose then I have a sequence of pointed K surfaces. So what that means is I have K surfaces with a preferred point. Now, if the images of these preferred points don't go away to infinity, if they don't fly away to infinity, which is a very normal condition to require in any sort of Artzellert-Scoli type theorem, then there exists a complete pointed immersed surface, S infinity, E hat infinity, living inside the unitary bundles. It's very important. Everything happens upstairs, towards which this sequence converges, towards which a sequence of lifts subconverges in Chigall-Gromov sense. So if I have a sequence of K surfaces, I do not know if these K surfaces converge, but I know that their lifts converge. So I need to forget that there are surfaces in hyperbolic space. However, Francois goes a little bit further because we have this problem that we don't know if this limit is necessarily the lift of a K surface. So we need to address this. And we get the second part of Francois' result, which is Francois' dichotomy. First, we take a complete geodesic in H3. We consider its bundle of unit normal vectors, so this is a cylinder. And we say that SE hat, which is an immersion inside the unitary bundle, we will call it a curtain surface whenever it covers the bundle of unit normal vectors over some complete geodesic. Well, not many of these are just covers of cylinders in the unitary bundle. And this is the second part of Francois' view. It tells you that if your Chigall-Gromov limit of surfaces is not the lift of a K surface, then it has to be a curtain surface. So this is very nice. If I have a sequence of K surfaces, I look at the lifts. I know that the lifts converge. Now I have two cases. Either the limit of the lifts is a curtain surface, so it's a cover of some cylinder, in which case its geometry is very easy to understand, or the limit of the lifts is a K surface, or it's a lift of a K surface, in which case it's something I'm looking for. So either way, I've won. It's a very powerful result. Right. So how do we use Francois' compactness result? Well, the main takeaway that I want you to take from this is that with Francois' compactness theorem, the only thing we require in order to get a nice compact, well, modulo a number of other details, the main thing we require in order to get a good compactness result is that the images of these base points remain within some compact set. So we need to find a compact set that contains the images of our base points. This is what we're aiming to do from now on. How do we do this? We now use the theory of flat conformal structures, flat conformal surfaces. In particular, we're going to use an object known as the Kulkarni-Pinkall metric. I'd like to say in passing that the Kulkarni-Pinkall metric, which we'll see presently, is a nice construction, but it's one of these objects that is not used very much. It's one of these things which is nice to look at. It's a bit of a curio, but I'm not aware of many places where it is actually used as an integral part of a proof of some result. So the result that I'm going to show to you today, the proof that I'm going to show to you today, is a nice application of the Kulkarni-Pinkall metric. And in fact, you'll see that the proof is remarkably simple using the Kulkarni-Pinkall metric once you have the right perspective. It's really a question of putting everything together in the right order. When you put everything together in the right order, everything falls into place disturbingly easily. Always upsetting, because if you want to write a paper and make it look sophisticated and you get a simple proof, it's a bit embarrassing. Anyway, I'm going to define a flat conformal surface to be a pair, S phi, where S is a surface and phi is some locally conformal map. So you see, and we will say that two flat conformal surfaces are equivalent whenever there exists a diffeomorphism, a conformal diffeomorphism, mapping the one to the other. So there's a sense of déjà vu here, and that should not be surprising. Asymptotic Plateau problems and flat conformal structures are trivially synonymous. I didn't want to introduce flat conformal structures at the beginning of the talk so as not to confuse you. But from now on, we're going to accept that an asymptotic Plateau problem is the same thing as a flat conformal structure. These things were studied considerably by Kulkarni and Pinkall in the 80s and the 90s. And the way to study a flat conformal structure is to look at its conformal disks. So what is a conformal disk? A conformal disk in a flat conformal surface is given by a pair dA, where D is any disk inside the Riemann sphere, and alpha is a conformal map sending D into S, whose composition with phi is equal to the identity. So given that phi is a locally conformal, it's a local diffeomorphism, so we know that these things exist everywhere locally, everywhere locally about every point. And it turns out that the set of conformal disks of a flat conformal structure contains all the information you need to recover the geometry of the surface. So the geometry of your surface is encoded, in fact, in the combinatorial structure of the family of conformal disks inside your flat conformal structure. Give me a second, I just need to drink something. So now we get to the Kulkarni-Pinkall metric. Just a second. Suppose I have a disk in the Riemann sphere. I will denote by G as Poincare metric, which, as we know, is a complete hyperbolic metric. And we can now define the Kulkarni-Pinkall metric G phi of my flat conformal structure like this. So this looks rather complicated, so I'm going to do a little diagram just to make everybody's life easy, because it's an important concept. So I have hyperbolic space. This is the ideal boundary of hyperbolic space. I have a surface, an abstract surface here, and I have a local diffeomorphism which sends phi into hyperbolic space. Now I take a disk in hyperbolic space, D, and I have a function alpha which sends my disk into an open subset of S, which has the property that phi composed of alpha is equal to the identity. So if I take a point here, it's sent a point here, and it's sent back here. This is a conformal disk inside my flat conformal surface. Now, I have the Poincare metric of my disk. This is defined here. I can pull back this Poincare metric. This gives me a metric over this open subset of my surface S. Now, every single one of these pullbacks is going to be conformal. So when you're dealing with surfaces, the space of conformal metrics at any point is just a line. It's well ordered. So you can talk about the infimal element. So you can talk about the infimal metric. So you take the infimum over all, for any point X in my surface, I will take the infimum over all conformal disks containing, whose image contains this point of the pullback of the Poincaré metric at that point. If we compare this formula that I just wrote down to what we have here, you'll see that this is the definition of the of the Kulkarni-Pinkall metric. This thing looks a bit messy, but it's actually very nice. It's a complete metric of type C11, curvature defined almost everywhere, and curvature taking values, well, in the two-dimensional case, in the closed interval between -1 and 1. Also of importance to us is the Kulkarni-Pinkall form. And the Kulkarni-Pinkall form is just the area form of the Kulkarni-Pinkall metric. So, what do Kulkarni-Pinkall show? Well, Kulkarni-Pinkall show that if your flat conformal structure is not equivalent to one of these two, that is the whole Riemann sphere or the whole Riemann sphere minus a point, then the Kulkarni-Pinkall metric is positive, definite, and complete. So I would have liked to have talked a bit more about that, but I see I'm beginning to run out of time. So what Kulkarni-Pinkall's result involves constructing what they call maximal conformal disks. And maximal conformal disks are defined intrinsically in terms of the conformal structure. I have a little figure here. The point is that if you have a flat conformal structure and a conformal disk, you can talk about the points of intersection of the boundary of the conformal disk with the boundary of the flat conformal structure. That's very informal because your flat conformal structure doesn't necessarily have a boundary. Then you can look at the convex hull with respect to this, with respect to its hyperbolic structure of this set of points, and you can show that your disk is maximal, about maximal for your initial point X, if and only if that initial point lies in this convex hull that you've constructed. And then you can then show with a little bit of work that there exists a maximal disk if and only if your flat conformal structure is not of this type. All very well. So you can look at Kulkarni-Pinkall's paper, or you can look at my review that I wrote for Papadopoulos, where I explain this in more detail. But the important point for us is that except in these exceptional cases, the Kulkarni-Pinkall metric is non-degenerate and complete. But now we're going to get to the interesting bit. And I know that some of you here are going to find this quite familiar, or relatively familiar. We're going to look at the geometry of open horribles because we want to use the Kulkarni-Pinkall metric to control the geometry of our case surfaces. So we start with an open horrible in H3. So we know that the open horrible is a sub-level set of a Horo function. So we know that an open horrible, it has the, it intersects the ideal boundary of H3 at a single point. I have a figure here. For those of you who are not used to hyperbolic space, an open horrible in the upper half space is simply a Euclidean ball in the upper half space, which meets the plane just tangent to the plane at height 0. So I'm going to call this point of intersection the asymptotic center of my horrible. Now, I'm going to do the following construction. I take an open half space, any open half space, which is an exterior tangent to my horrible at some point. So here we have my point Q. Here I have a totally geodesic plane. And so the open half space is the inside of this plane. I let D denote the ideal boundary of this half space. So D is going to be this disk in the ideal boundary, which is the ideal boundary of my open half space. And then what I'm going to do is I'm going to look at the metric, the Poincaré metric of this D at the point P. So this should be GD at P, does not depend on Q. Okay. So what that means, the Poincaré metric of this disk evaluated at this point P does not depend on the point Q chosen. So I'm going to define omega P to be GD of P, this should be P, not Q, composed of J to turn it into a form. And I'm going to call this omega the asymptotic curvature of my horrible. It turns out, why do I call it asymptotic curvature? Because it behaves like curvature. So it turns out that open horribles in H3 are uniquely determined by their asymptotic curvatures and their asymptotic centers. So what this means is that I can parameterize the space of open horribles in H3 by the space of two forms over the ideal boundary of H3. So for any two form in the ideal boundary of H3, I define B omega P to be the open horrible of asymptotic center P and asymptotic curvature omega P. And this gives us the C0 estimate. Suppose I have a quasi-complete IC immersed surface, infinitesimally strictly convex immersed surface in H3. Note that I'm not using the curvature condition here. I'm just using quasi-completeness and the fact that it's infinitesimally strictly convex. Let phi be its asymptotic Gauss map, let omega denote the Kulkarni-Pinkall form. And for all x, for every point in my surface, the image of x under E is contained in the closure of the horrible defined by this form. So what does that mean? Well, observe that omega x is a form of my over my surface. The push forward of omega x is going to be a two form over at some point of the boundary of hyperbolic space. We've already seen the two forms over boundary points of hyperbolic space to find horospheres. So I have a horosphere here, and I take the closure of it. Now, this result really requires quasi-completeness. It does not work if you're not quasi-complete. So the schematic of the proof is shown in this diagram here. Once again, it's disturbingly simple once you put everything together the right way. So I have my surface sigma. I take a point. I look at the tangent plane. I look at the totally geodesic plane bounded by that, a tangent to sigma at that point. And I look at the horosphere, which is, whose asymptotic center is the image of P under the asymptotic Gauss map, and which is tangent to the totally geodesic plane and to sigma at the point P. Now, the objective here is just to show that the whole of this disk is actually contained in the image of phi. So what you have to do is you have to show that every geodesic lying in this open half space, so above this totally geodesic plane, projects down to something onto sigma. And you can do that, and you use infinitesimal strict convexity to do that. And what that tells you then is this entire disk is contained inside the image of phi. It's contained within the flat conformal structure defined by my asymptotic Gauss map phi. And in particular, this means that this chap here, this horrible, which is defined by omega, is going to be, it's going to be bounded above by the Kulkarni-Pinkall form. Why is that? Because the Kulkarni-Pinkall form is an infimum. It's an infimum of curvatures of horribles contained inside my flat conformal structure. That is, the Kulkarni-Pinkall form is a measure of the largest horrible contained within my flat conformal structure. That's the idea. So we have our compactness result. We have most of our compactness result. We have an almost compact set containing the image of this point. It's not compact because it goes to infinity at Q. But this region here near Q is actually quite easy to exclude using the geometric maximum principle. So it's this C0 estimate here that is enough to give you points which lie within a compact set, and then you can apply Franz's compactness theorem. In actual fact, you need a little bit more than that. This isn't all you need. You need to do a little bit of, naturally it's not sufficient to catch a fish for the fish to bite. You need to reel the thing in. So you need a little bit more information. And one of these properties that you need is uniform quasi-completeness. So Here we have a lemma. I have to admit that my literature research is a little bit shaky. I published this preprint quite recently, so I might be a little bit, I might have missed something in the literature, but we have this lemma. I think, I'm not sure if it's been proven before, but it's quite a simple lemma. The point is that the Kulkarni-Pinkall metric is bounded, the Kulkarni-Pinkall metric is in fact a lower bound for this chap, which when you're locally strictly convex by the Cauchy-Schwarz inequality is a lower bound for this chap. Now this guy here is an old friend for some of us. This guy here in the middle is nothing other than the horospherical metric, which was introduced by Schlenker and studied in a nice paper in the Journal of the European Maths Society by José Espinar, José Galvez, and Pablo Mira. So I have 5 minutes. Give me a second. The sun has risen and is now shining in my face. Right. So I have 5 minutes. I just want to say something about a nice linearization of this result. So for this, we need the Schwarzian derivatives. So we take a domain in C. We imagine we have a locally conformal function, sending my domain into the Riemann sphere. So there's a theory of there's a theory of locally conformal functions. The theory of locally conformal functions yields what is known as the Schwarzian derivative, which is always finite for locally conformal functions, and it's defined by this formula. This formula looks pretty weird when you first look at it, but it's actually very closely related to the projective structure of C hat. C hat is actually a projective space. And when you see the Schwarzian derivative as a projectivization of something, it becomes much simpler. So there's an old theorem, I don't know who proved it, I think it's folklore, which relates Schwarzian derivatives to locally conformal maps. It's a back and forth result. It says that if you have a simply connected domain, then for all f from this omega into C, there exists a phi, and exists a function phi, locally conformal, with Schwarzian derivative is equal to f. So this inverse problem can always be solved. Furthermore, the function is unique up to composition of a Mobius map. So what this means is in my hyperbolic and elliptic convergence, hyperbolic and parabolic convergence results, existence results, I can take the Schwarzian derivatives of these guys and use the Schwarzian derivatives of these guys to parameterize the space of K surfaces. So let's have a look at what that gives me. This gives me a rather tasty little expression. We have first the hyperbolic space, which states the following. For all k in 0, 1, and for all holomorphic functions sending the disk into C, there exists a K surface E, sending the disk into H3, whose asymptotic Gauss map phi E has Schwarzian derivative equal to F. Furthermore, modulo post-composition by isometries of H3, which comes from this part of the recovery of phi from F, which comes from this part of this theorem. Modulo post-composition by isometries of H3 E is unique and varies continuously with F. And then we have the parabolic case. The parabolic case is similar, but different in an interesting way. For all k in 0, 1, and for all non-constant holomorphic F, there exists a K surface E. This has asymptotic Gauss map, has Schwarzian derivative equal to S. The exceptional cases in the parabolic case are exactly those for which the Schwarzian derivative is constant. These nice two linearized parameterizations of the space of K surfaces. Furthermore, in the parabolic case, modulo post-composition by isometries of H3, E is unique. But note that we don't have continuity. And as I said, I suspect that the solution does not vary continuously with the data. So this is where I would like to end my talk. Just like to say that despite all these problems that we're encountering, that we're living through at the moment, we all know that cycle of life, which has gone on for centuries, will continue for centuries, unaffected by human problems. And right now, back home in Scotland, it's lambing season. This is the time of the year when all the little lambs are born, and when you drive through Scotland in April or early May, you'll see fields full of little lambs, happy little lambs bouncing all over the fields. It's a delightful sight to see. So I thought I would finish this talk by sharing with you a picture of two recently born lambs from my little village in Scotland, where I come from. So thank you very much for having listened to my talk.